So right below our sketch with our zeros being x equals -2, x equals 3, x equals 4, we have example 1. We're going to call this example 1 mainly because it is example 1, even though it's not written that way on your packet that you have in front of you. So you may just want to write in example 1 because it's going to kind of go along with the example 1 information. So right above, we took our group warm-up and we kind of sketched what that would look like if we knew our zeros were -2, 3, and 4. In this case, we found the local maximum and we found the local minimum points. In example 1, from here, we're also looking back at the general equation for that polynomial in our group warm-up, but let's suppose that we do not have a graph of this function. Okay, we just are given the general form of this polynomial function, but we're not given the graph and we're not going to find the zeros of this graph. How can we take this information only and figure out how many turning points we have of this function? Above, if we obviously have the graph, we can count how many turning points we have. We have from a positive y movement to a negative y movement, that maximum is 1 turning point. And then from a negative y movement to a positive y movement, we have a minimum, which is our second turning point. So we know by our graph we have 2 turning points. But if we don't have the graph, it's a little harder to figure out how many turning points we have. So to do that, we have a little formula that we can kind of memorize in the back of our head to pull when we're given a situation like this. In our general function, at most, how many turning points does this function have? So at most, how many turning points does this function have? And we find that by first locating the degree of our polynomial. And if you remember, the degree of your polynomial in standard form should be the first value that you have. If it's not in standard form, obviously your degree is the one that has the highest exponent, the value of that highest exponent. So in this case, we are in standard form. We have x to the 3rd power leading us off, so we know we have a cubic function. So we know our degree is 3. And we find this, at most, how many turning points do we have? We find how many possible turning points we have by always taking our degree, whatever value that is, minus 1. That's our little formula to find out how many turning points that our function has. So in this case, since our degree is 3, 3 minus 1 gives us a turning point of 2. And we know that because if we look back to the original graph, we have 1, 2 turning points on our graph. But in this case, that's at most how many turning points that we have. Okay? But how can we determine the exact number of turning points? At most means the very highest number of turning points. So we obviously could have a function like this that we get a turning point value of 2, but it has less than that. Okay? But how can we figure out the exact number of turning points? The exact number of turning points happens if and only if our degree is equal to the number of x values, or are equal to our number of zeros, I should say. So in this case, our degree is 3. We know we have 3 zeros. So since these two are equal to each other, we know we have 2 turning points of our graph. So let me do that since I wrote that without you guys being able to see it. The exact number of turning points happens if and only if our degree value is equal to the number of zeros on our graph. So, for example, in this example 1, we have a degree of 3. We know from our graph and from our first warm-up together that we have 3 zeros. Therefore, since these two numbers are exactly the same, we have exactly 2 turning points on our graph. And that can be shown again by looking back above to our sketch of our graph. Okay, so let's move to the next sheet of paper where we have a Now You Try. This is kind of like your example 1, but since we built on example 1, you guys are going to have a chance to work on these yourselves. So from here on out, I want you guys to pause after we do letter A together, I want you guys to pause for letters B, C, and D. We'll come back in the next video and go over the answers. But I want you to try those 3 problems on your own once you kind of get the hint as to what is being asked in letter A. So in letter A, we're given a polynomial function. In this case, it's already half done for you. It's already factored, so we don't have to go through and do long division and factor this. It's already factored for you. From here, they want you guys to find the following information. They want you guys to list the degree, the number of distinct zeros, and the number of possible turning points. Okay, so in this case, this is already factored down for us, right? So I want to go through and I want to set each of my zeros, or these x values, these groups, equal to 0 to see what my zeros are. So my x on the outside, each of these groups are getting set equal to 0. So my outside x gets set equal to 0, x minus 1 gets set equal to 0, and x plus 3 gets set equal to 0. If I go through and solve, obviously x is equal to 0 doesn't change, x is equal to 1, and x is equal to negative 3. I have 3 distinct zeros, okay? Since I have 3 leading x's, if I were to multiply this through, so for example, and you don't have to do this on all of them, but the idea is if I foiled these 2 groups together, I would have x times x squared minus 2x minus 3 if I foiled these together. And if I go one more step and multiply my x all the way through, this polynomial in expanded form would be x cubed minus 2x squared minus 3x. That would be my expanded value. But these 3 zeros, we're taking our factored forms and breaking them down, setting them equal to 0. So I know I have 3 distinct zeros here. Distinct meaning that they're all different numbers. So if I expanded this out, I know that my 3 leading x's would give me a cubic function. So my degree